All right, ladies and gentlemen, welcome back. So now that we have a basic understanding of the geologic record and sort of just where life in general fits into Earth's history, let's start talking about what we know as the origins of life. So if you remember your cell types, prokaryotes are the ones without the nucleus, without the organelles. So in very many respects, they are more simplistic than the eukaryotic cells with all of that internal structure. And so when we look at the fossil record, the oldest known fossils that we find are these stromatolites, these big mats or masses um, that are composed of many layers of bacteria and sediment. And these show up in our fossil record around 3.5 billion years. Interesting thing about these stromatolites is that these are large, complex bacterial communities. So, by finding these stromatolites at this point in time, we find it reasonable to suggest that life must have begun before this, where they were living as individual isolated organisms as opposed to this more complex community structure. And so, there's suggestion that life probably began somewhere as early as 3.9 billion years because that individualized life pattern would have predated this community structure that we see in these stromatolites. So, if we talk about going all the way back to how life would have gotten started, we talked about the primordial soup model and the Miller-Urey experiment to give us some credence to say that the oceans probably were where life began because that's where macromolecules would have first been capable of forming and recreating themselves. We talked about those protocells, so those lipid layers that would have surrounded some of those molecules gave us the ability for some self replication and some early metabolic chemical reaction processes. Somewhere along the way, genetic material comes into play, so there's accurate replication. And then eventually, all of this sort of aggregates together to get us these first prokaryotes. Once we get to this, now these organisms are capable of producing all, if not most, of their needed compounds from the things that they find in their environment. Okay. So, the appearance of our first autotrophs, right, organisms who are capable of producing things for themselves, energy for themselves, as opposed to those early heterotrophs that would have needed to consume things out of their environment. Regardless, collectively, these original prokaryotic autotrophs and heterotrophs would have been Earth's sole inhabitants from at least 3.5 to 2.1 billion years. So, a pretty significant chunk of Earth's history was just these prokaryotes, whether they were able to create their own energy, more likely from a chemosynthetic standpoint, so using chemicals in their environment, at least initially, and then eventually we get to photoautotrophs, and then the heterotrophs being there as well, just consuming things from their environment to create their own energy. Speaking of photosynthesis, this is going to be a huge, huge turning point, not only for life, but it's also going to reshape Earth as we know it. So let's talk about this idea of this oxygen revolution. So, most of the atmospheric oxygen that exists on Earth has biological origin. Where is it coming from? It's coming from this water splitting step of photosynthesis. So, that initial photosystem that brings in energy from the sun um, shifts electrons around within chlorophyll molecules, and those electrons need to be replaced in order for that photosynthetic process to continue working. So, where do these organisms get those extra electrons from? They go through and they split water. They get hydrogen positive atoms because they've yanked the electrons off, and then oxygen also comes off as a byproduct. So the photosynthetic bacteria aren't using the oxygen for their own purposes. So instead, it just ends up sitting in their environment. And we know that when this process first evolved, most of that oxygen was dissolved in the surrounding water. It continued to bubble into solution until that solution was saturated with the oxygen, and then the oxygen started bubbling out of the oceans and ending up in our atmosphere. What's our evidence for this? We look through the geologic record, and there's a very distinct layer of rust, iron oxide. And we know that Earth's core is very much iron rich. So by not seeing that rust, not seeing that rust, not seeing that rust, and then all of a sudden seeing that rust layer, we know that oxygen must have started to become a common element. And as soon as we get iron plus oxygen, we get the rust. That rust is heavier than solution, so it would have fallen out into a sediment layer. And then we see rust layers from there. That's kind of what this picture is showing here. So once all of that iron was sequestered in that iron oxide, bound to that oxygen, any additional oxygen that was left in solution that didn't have the iron to bind to would have gassed out of the water, okay, would have bubbled out and eventually ended up in the atmosphere. And so we see that change in that rust layer around 2.7 billion years. So, what this implies is that cyanobacteria, which are our biggest category of photosynthetic bacteria, must have originated probably as early as 3.5 billion years because it would have taken time for that oxygen to sequester that iron before it started gassing out into the atmosphere. What we see in our geologic history in the rock layers in ice cores, which trap gases in themselves, which is pretty cool, is that there's this rapid increase in oxygen in the atmosphere from about 2.7 to 2.3 billion years. This is what we're talking about with this oxygen revolution. Interesting thing is that this oxygen revolution is going to have a huge impact on life and a huge impact on Earth itself. So it actually causes the extinction of a lot of prokaryotic groups during this time. Those that survive, however, end up adapting and most end up using cellular respiration to harvest energy. So let's back this train up a second. Why is this oxygen revolution such a big deal? Well, it's going to do a handful of things for us, and this might be some good side notes for yourself. First off, getting that oxygen into the atmosphere is going to end up causing that oxygen to react with other chemicals as well as solar UV radiation to produce ozone. We didn't have an ozone layer predating this. Once this oxygen revolution occurs, we've now got an ozone layer. And if you know anything about that ozone layer, its job is to protect us from UV radiation. That's what it does for us. It keeps our surface from being completely irradiated, which is why life can exist on land. Pre this oxygen revolution, all of life was stuck in the oceans. The water itself acted as its own UV filter, allowing life to exist. Once this oxygen revolution occurs, however, we now have that production of that ozone layer, and now we're going to set the stage for the capacity for land to now become a habitable zone as well. And so eventually we're setting up the ability for life to colonize land, which is pretty crazy. Before that, everything gets irradiated, we destroy DNA, we destroy RNA, and nothing can exist there. Second thing is this idea of cellular respiration. If you know anything about cellular metabolism, if you are not, scratch that, when you go to take sugars and convert them into ATP, right? Sugar into cellular energy, you really have two options: cellular respiration which occurs in most organisms, um, big organisms in particular, and even plants do cellular respiration. They take the sugars that they create and convert it into energy via cellular respiration. Your other option, which tends to be more bacteria, microbial organisms, although some bigger organisms, including us, can do this on a small scale, is fermentation. The big difference here comes to the amount of energy that you produce from both processes. When I look at cellular respiration, I'm making somewhere on the order of about 32 to 36 ATPs for every glucose that goes in. Okay, so 32 to 36 ATPs for every glucose for cellular respiration. When we're talking about fermentative processes, which is what most organisms would have been doing pre-photosynthetic evolution, they're only capable of making 2 ATPs per glucose. So fermentation is an incredibly inefficient process. Even cellular respiration is only maybe about 40% efficient. So we're making 36 ATPs from cellular respiration at 40% efficiency. Fermentation's terrible. We're making 2 ATPs for every glucose. So the ability for cellular respiration to evolve as part of this process as well, cellular respiration requires oxygen as part of its process, which is why it didn't exist pre the oxygen revolution. But once the oxygen is now readily available, cellular respiration had the capacity to evolve, and now we're able to make a lot more energy per glucose as a result. And so we get a more efficient process out of this revolution as well. And that's going to be huge because that is going to be what is necessary for larger organisms to start evolving. If we had been stuck with fermentation, we never would have gotten past microbial life because there's just not enough energy to sustain life in larger forms at 2 ATPs per glucose. You'd never stop eating if you could even consume enough at our size as humans to sustain all of our cells with only 2 ATPs per glucose. It just would be impossible.